4.3, we're going to take a look in this section at greatest common divisors and least common multiples. This is the last section in chapter 4. And to start with, we're going to define what that means. One half of it anyway. The greatest common divisors, GCD, also called greatest common factors. Those are interchangeable. It is the greatest whole number that divides all numbers in your set. And we're finally going to define a phrase that I've used across like 3 class periods now, relatively prime. Relatively prime describes 2 or more numbers whose greatest common divisor is 1, i.e., they have no common factors other than 1. Okay, they only divide by 1 in common. It does not mean that either of them have to be prime, by the way. They could both be composite numbers and still be relatively prime to one another. Let me give you an example. How about we do 15 and 8? That would work. 15 and 8 are both composite numbers, but there's no number that divides them both. Okay? So that they don't have to be prime to be relatively prime. It's a comparison thing, right? Okay. There are several different ways of looking at whether or not numbers have a greatest common divisor or a relatively prime. So we're going to spend the next bit of class period looking at methods for finding greatest common divisors. As with all the other methods we've seen and everything else, there's benefits and there's drawbacks to every single one. That's just the way things go. You give a little, you get a little, right? So we'll try and take a look at those as well. Intersection of sets is our first one. The intersection of sets method is to list all divisors of each value and then find the largest divisor that the values have in common. You're creating a list, like our pirates, right? We're creating a list. Now, if the number doesn't hit on a greatest common divisor anytime soon, this is terrible because your list could be forever long. That would be annoying. So this tends to work with numbers that are better with numbers that are smaller and that have a divisor in common pretty quickly. Okay, that's when it tends to work the best. So we're going to do an example. Our example is going to be 12 and 15. So we're not listing multiples like we were previously with our pirates or our baseball cards and things. It's not multiples, it's divisors. Now, we've done this before where we've taken the number and we've written down that it can be divided, right? 12 and 15, or 12 would be like 1 times 12, right? What's another number that would divide 12? 2 and 6. So we're just writing them in a list form. And they don't have to be listed like left to right. They can be in a little circle like we've been doing. What's next? 3 and 4. Okay, so that's 1 and 12. Or that's 12, excuse me. Now 15. So we would start with 1 and 15. And what else did we have? 3 and 5. Small numbers are fantastic for this method, because it doesn't take us very long to write out all the multiplication things that work to being multiplied to give you 12 or 15. And then we're looking for just the biggest number that's in both lists, and that is, what'd you say, Katie? 3. And so our GCD, or you could say GCF interchangeably, is 3. Intersection of sets. Okay? So the drawback is that it only works really nicely when it's small enough numbers to do this with. But one of the benefits is that when it has those kind of numbers, it's very fast. Okay? It's very quick to do. Method number 2, prime factorization. Prime factorization might be the most involved method, but it's definitely the most structured method too. It's got a lot of structure to it. That's why you see like step 1, step 2, step 3, right? Like that, okay? So step 1 is to construct the prime factorization of each number, which we've done. We did that back in section 4 too, either by a tree diagram or by the division by primes, right? Okay, where we divided by primes in like this division scaffolding. Step 2 is to choose all prime factors that are common to each factorization. So do they both divide by 2? Then it gets listed. Do they both divide by 2 squared? Then it gets listed, right? So that's not a good example. Let me just stick with 2 for a minute. We'll get to the squared in a second. So whatever prime numbers divide, both of them get included. And then you list those primes with the smallest exponent from each of the lists that you're working with. That's step 3. And then step 4 is to find the product of what remains. Like multiply it back out, typically, is what they're looking for. Okay, so like we could do this with these numbers, but it would be overkill. Do you see what I'm saying? Like, these numbers were small. There's no reason we would want to do prime factorization. Not because we can't, but because it's just not necessary. But these numbers are a bit bigger. Yeah? 400 and 360 would probably not be the best way to do it with the intersection of sets method as before. So what we're going to do is we're going to do our division scaffolding. So we're going to do 400. 400 divides by 2 and gives me 200, which divides by 2 and gives me 100, which divides by 2 and gives me 50, and divides by 2 and gives me 25, and I get 5 and 5. And if I'm listing all this out, how many 2's do I have? 4? 2 to the 4th, and 5 squared. Does that look okay?
So can you do that with the tree?
You can. I'll do the other one with the tree, since you asked. Okay, 360. So let's do 360 with the tree. So if you did 360, you probably would not do 2 and something. You would probably do like 10 and 36, because it ends in 0. Trees tend to work better if you do bigger numbers to divide them, usually composite numbers, so we'll do that. 10 is 2 and 5, and to try and keep track of them, I'm going to circle them when I get to primes. For 36, you might do 6 and 6, you might do 9 and 4. Just for fun, I'm going to do 9 and 4. 9 and 4, neither one are primes, so I've got to keep going. 9 would be 3 and 3. There's some primes. And then 4 would be 2 and 2. Okay? So it would be really weird to do what I just did and do one of them division and then one of them with a tree. But pick your favorite and just do both of them the same way. It's fine. All right. Well, what do we get at the end? Well, there's 2's. How many 2's are there? 3. What else are there? There's 3's. How many of them are there? 2. And there's 1 5. Is that it? Okay. So this is step 1. I did prime factorization for each number. Step 1 is the most time-consuming step, okay? Step 2 is just identifying the numbers that are in common to these lists. So if I look between this list and I look at this list, what numbers do you see that are in common? 2 and 5. Now, the biggest mistake people tend to make is that they forget the next step. They just stop there and say, look, it's 10, and they move on. You can't stop there. That's just step 2. Step 3 now says to see how many of them there are, okay? How many 2's do they really have in common? Is it just 1? If so, great. If it's not, you have to list that. So how many 2's do they have in common? Well, the first one had 4 2's, and the second one had 3 2's. So how many 2's do they have in common? 3. Each of them have at least 3 2's. So it's 2 cubed. How many 5's do they have in common? That one's just 1. And then the last step is to simply multiply what you have here. So this is 8 times 5, or 40. So 40 is the biggest number that divides both of these numbers. Okay, definitely the most time-consuming process, but here's something else about this that makes it a plus. This is the most useful method for extending the knowledge into algebra, because you have variables, and we have variables to powers, and you're looking for things that are already in a prime factored kind of form. This one's the best extension problem into further mathematics. Okay? That's important to know. It is very valuable. All right, let's try another one, though. Next one is called division by primes, which sounds kind of like prime factorization, but it isn't the same. It has some similarities, but it isn't the same. We write the numbers in a row, and we divide by a common prime number, common prime factor. We divide the quotients by a common prime factor, and we keep doing this division until there's no other common prime factors, and the greatest common divisor is the product. Truthfully, this is probably my favorite one, because it's the quickest and it yields the most intuitive structure to me of all of them. Okay, so it is both quick and structured. So I have different numbers, but we could have used the same numbers. In fact, let's just change it and use the same numbers so that you can see that it works. Let's do 400 and 360. We need a prime number that divides them both. What prime number will divide them both? 5 will. Okay, cool. We're going to start with 5 on this one. It doesn't have to go in order of anything. 5 will be great. So if you do 400 divided by 5, what are you going to get? 80. And if you do 360 divided by 5, what are you going to get? 72. Okay, cool. Okay, 80 and 72, do they divide by any more primes? Yes, they do. They can divide by a 2. So now we have a 2. What is 80 divided by 2? 40, sorry, thank you. And 72 divided by 2? 36. Do they divide again by something? Another 2. 20 and 18. And then? Another 2. And that gives me 10 and 9. 10 and 9, do they divide by anything? No. And so right over here, there's your answer. And it's all right there. You can multiply it back out. You can see that there's 3 2s and a 5. That's the same 40 that we got before. Cool, right? Okay, we will pick back up next time with the Euclidean algorithm, which is our last divisibility, or our last one for divisibility for common divisors, and then we'll move on to least common multiples.